Hello everyone, welcome back for another SVSU Math and Physics Resource Center tutoring video. Once again, my name is Brendan and I'm going to be your tutor. And for this video, we're going to go into finding the interval and radius of convergence for a power series example. Hope you guys enjoy. Alright, let's jump right into this power series example. So what we're going to do is we're going to run the ratio test on this power series, and we're going to use the criteria for the ratio test to see what values of x make this converge. Okay, so the first thing for the ratio test I'm going to do is I'm going to identify my a of n term. So this is my a of n term. And then I'm going to go ahead and write out my a of n plus 1 term. Okay, so let's see what we have. So it looks like we're going to end up with a n times 2 to the n plus 1 divided by 4 times 3 to the n plus 1, and then multiplied by 2x plus 17 to the n plus 1. Okay, so then let's simplify this and see what we get. It looks like we're going to end up with a n to the 2n plus 3 if we distribute the 2 through and then add the extra 1 at the end, divided by it looks like we're going to end up with a 4 to the 3n plus 3. And then this is going to be in the numerator, so 2x plus 17 to the n plus 1. Okay, so now that I have my a of n plus 1 term, we can go ahead and run the ratio test. So if we remember, the ratio test is the limit as n approaches infinity of the absolute value of a of n plus 1 divided by a of n. Or we can write it as the limit as n approaches infinity of the absolute value of a of n plus 1 multiplied by 1 over a of n. And then this is the one that we're going to use just so we don't have to write out a double fraction. So we're going to have the limit as n approaches infinity of the absolute value of a of n plus 1. So that's the term we just simplified. So that's going to be the n to the 2n plus 3 times 2x plus 17 to the n plus 1 divided by 4 to the 3n plus 3, and then we're going to multiply by the reciprocal of a of n. So that's going to be 4 to the 3n divided by, looks like we have a n to the 2n plus 1 times 2x plus 17 to the n, absolute value. Okay, and then so what we're going to want to do is just simplify as much as we can. So we can use our exponent rules, and we can imagine this being like a n times n to the 2n times n to the third, right? And then a 4 to the 3n times 4 to the third, right? So then I'll be able to cancel out some terms. So I have the limit as n approaches infinity of the absolute value. So this n to the 2n is going to cancel with the n to the 2n there, and we're going to be left with a n to the third on the top and an n to the first on the bottom. So the first comes from this plus 1 that's in the exponent, and the third comes from this plus 3 that's in the exponent. Okay, so then another thing I'm going to be able to do is I'm going to be able to cancel out the 4 to the 3n, 4 to the 3n, and then that's going to leave me with a 4 to the third from this exponent, this plus 3 in the exponent. And then I'm also going to be able to cancel out this 2x plus 17 to the n, and then this n that's in the exponent here. So then on the numerator, I'm going to be left with a 2x plus 17. Okay, and so since this limit is in terms of n, what we can do is for our x values, this will just be a constant. So we can pull this constant, assuming that we have an x value, we can pull that constant out of the limit. So it's going to be 2x plus 17, don't lose our absolute value bar though, times the limit as n approaches infinity of, it looks like we're left with n squared on top and 4 to the third on the bottom. Okay, and so when we evaluate this limit, when we plug in our infinity here, we're just going to have infinity squared over a constant. So this is going to be infinity. Now, if you remember from the ratio test, we want this to be less than 1. Well, we're wondering how are we going to get this less than 1 is if every time we take this limit here, this is going to be infinity. Well, actually, there's only going to be one way we can do that. And the only way that we can do that is if we can get this piece to be equal to 0, right? That's the only time we're going to be able to get this to be less than 1. So we have 0 times a positive number, a really positive number. Okay, and so anytime this isn't 0, so say x is anything other than what makes this front constant 0, then we're going to get a non-zero term here, a positive non-zero term, times a really big positive number. So we're definitely going to be greater than 1. So let's go ahead and set this equal to 0 to find our x value. So 2x plus 17 is equal to 0. So we're going to get, looks like x is equal to negative 17 over 2. So then that tells us that we only have one spot when our power series converges, and that's going to be at x is equal to negative 17 over 2. So this is our interval of convergence, this negative 17 over 2. And when we only have one position or 1 point when this power series converges, that tells us our radius of convergence is 0. Okay? So just to kind of recap, we went through with the power series, we did the ratio test. After solving through for the ratio test, we wanted to see what values of x makes our power series converge, or our series converge, which means that we want our ratio test to be less than 1. And so the only time that this is less than 1 is when we have x is equal to negative 17 over 2, so 1 point. And so then that tells us that our radius of convergence is equal to 0. All right, hope you guys enjoyed the video.